This presentation covers a combination of circuits, including both series and parallel paths. Here we combine the two configurations we've already discussed in the same circuit. Here's an example of a series parallel circuit. It looks really complicated. Here we have over on the far left the voltage source of 9 volts. We have a total of 5 resistors comprising this series parallel circuit. And so the first thing to do is to draw all of the currents, or label all the currents, and I've done that. And typically this is the direction in which they would flow. Although if you pick an opposite direction, you will get a negative answer. So let's go ahead and see how one would evaluate a circuit of this type. We can solve this circuit using the same techniques we used on solving series and parallel circuits. We just have to go about it in an organized way, a process, if you will, starting at the end of the circuit and working backwards. So the first thing we do is combine R4 and R5 in series to get an equivalent resistor of 740 ohms. This resistor then is in parallel with R2, so the combination of R2 and 740 is 749 times 470 divided by 749 plus 470, which is equal to 372 ohms. Now the combination of R4, R5, and R2 is a resistor of 372 ohms in series with R3. So R3 plus 372 is equal to 1052 ohms. All that is left is to find the parallel combination of 1052 and R1, which is 220. We can do that using the same technique, and we get a total of 182 ohms. So we have collapsed our circuit and reduced it to the 9-volt source and an equivalent resistance load of 182 ohms. Applying Ohm's law, we solve for the total current seen by the source. That's 49.5 milliamps. This is the current that will be drawn from the 9-volt source. This in itself tells us how much total current the whole mess draws and enables us to determine the amount of total power consumed as well. The power dissipated in the circuit is 9 volts times 49 milliamps, which is 445 milliwatt, which is pretty close to 1/2 watt. In some cases, this may be the only question asked. If so, then we're finished. But a complete analysis would require determining every voltage from every current in the original series parallel network and perhaps the power dissipation in each resistor. Let's go ahead and begin re-expanding the network to its original form, finding currents and voltages as we go. Here's what we know. The supply voltage is 9 volts. The supply current is 49 milliamps, and the voltage across R1 is 9 volts as well. We can easily find I1 using Ohm's law. It's just 9 volts divided by 220 ohms, or 41 milliamps. Using Kirchhoff's current law, we know that I source is equal to I1 plus I3. So we can, by subtraction, obtain I3. That's 49 minus 41 equals 8 milliamps. So I3 is 8 milliamps. The voltage drop across R3 is therefore 8 milliamps times 680 ohms, which is 5.4 volts DC. If this is correct, then the voltage across R2 is 3.56 volts DC, and I2 is 3.56 volts divided by 470 ohms, which is 7.5 milliamps. Using Kirchhoff's current law a second time, we know that I4 equals I5 equals I3 minus I2. 8 milliamps minus 7.5 milliamps is 0.5 milliamps. Using Ohm's law a final time gives us the voltage drops across R4 and R5, which turn out to be 0.9 volts and 2.8 volts, respectively. As a check, we can use Kirchhoff's voltage law to sum voltages around the R2, R4, and R5 loop. We get an error of about 0.14 volts instead of 0 volts. Not bad considering the rounding in our calculations. Out of 9 volts DC, that's an error of 1.5%. We now know all the currents, voltage, and resistor values in the circuit. Finding the power in each resistor is easy. Go for it. Here's a series parallel circuit And here is the circuit we've been working from or with, and you can see the solutions in this diagram.